Hello, so this is video number 1 of section 7.1. And this is our last chapter of the semester. We've got 3 sections I want to cover in chapter 7. It's hard to believe that 8 weeks has gone by so quickly, but time flies when you're having fun. So just jump right into it. So we're going to start by introducing a new definition, which might be one of the shortest definitions we've introduced thus far. But as we'll see, the matrices that satisfy this definition of being symmetric are really, really interesting. And like what we're kind of going to talk about really brings together a lot of what we've done in chapters 5 and 6. So a matrix A is symmetric if it is equal to its transpose. So I've got an example here of what a symmetric matrix looks like, but before going on to that, I want to quickly talk about the problem I have on the board, which is more of a fact, but I think this is sort of good, good practice using the transpose and such. So show that every symmetric matrix must be square. So pause the video, kind of think about, the relationship between A and its transpose for a second, and try and work through the problem. All right, so this is actually, it's a relatively short solution. So remember, if A is an m by n matrix, then a transpose is an n by m matrix. And since A is equal to its transpose, this means that M has to equal N. Otherwise, those two matrices can't be equal. So it just sort of follows from how the dimensions flip around when we take the transpose of a matrix, and the fact that if these two matrices are going to be equal, then of course the dimensions have to be equal. So one thing we already know about symmetric matrices, they have to be square n by n matrices. I tend to like square matrices the best because we can start talking about things like eigenvalues and invertibility. We can start calculating determinants and all that. So we want to show that this matrix is symmetric, and then we want to calculate its eigenvectors and its eigenvalues. So I have a reason for wanting to do this. As we'll see, the eigenvectors in particular of a symmetric matrix are very interesting. So I kind of have you can tell what symmetric matrices look like. So the way we could calculate this, well, when I take the transpose of a matrix, of a square matrix, the diagonal stays fixed. And then remember, you're kind of, the rows become the columns and the columns become the rows, right? So you can see here, this is column 1 of A, column 2 of A is 1, 5, 1, column 3 of A is 5, 1, 1. And so sure enough, calculating the transpose, we get the same matrix, so this matrix is symmetric. The way I like to kind of determine if a matrix is symmetric is by looking at the reflection across the diagonal. I think I erased a 1 there, but notice if I reflected this matrix across its diagonal, it would stay the same, right? That is, 1 would reflect to 1, 1 would reflect to 1, 5 would reflect to 5. The math way of saying that the matrix is equivalent if you reflect it across its diagonal is that the entry in the ith row in jth column should be equal to the entry in the jth row in the ith column. So any one of these 3 things is sufficient to determine if a matrix is symmetric. You're just, again, reflecting across the diagonal. You could just calculate the transpose and show that it's symmetric, or just show that, the entry in row ij is equal to the entry, or the ijth entry is equal to the jith entry. So I say calculate the eigenvalues, but I've actually just given the eigenvalues to save time, since it's not really the eigenvalues we care about in this problem. So I ordered them as 7, -4, and 4. So notice, in particular, this matrix is also diagonalizable because it has 3 distinct eigenvalues and it's a 3 by 3 matrix. So what we want to do now is calculate the eigenvectors for each of these eigenvalues. Right off the bat, I can tell you that an eigenvector for lambda 1 equals 7 is 1, 1, 1, 1, 1, 1, because all of the rows add up to 7, right? So remember, that's kind of like just a quick way. If the row sums are all the same, that row sum is an eigenvalue corresponding to eigenvector 1, 1, 1. -4 and 4, unfortunately, we don't have quite, we don't have tricks that we can use in that way, so we're going to have to, and actually I think I'm going to erase this for now just so we can have more room. For these two vectors, or these two eigenvalues, we'll have to calculate the eigenvectors the normal way. So we want to row reduce the matrix A minus -4 times I, which is equal to the matrix where I subtract -4, or add 4, I guess, to all of the diagonal entries. And just to save time, I'll just tell you what the row reduced echelon form of this matrix is. So this row reduces to the matrix 1, 0, 1, 0, 1, 0, 0, 0, 0, which, remember, finding the eigenvector for this eigenvalue, -4, what we want to do is look at the homogeneous, or the solution, or the parametric vector form solution, right, to the homogeneous system of equations that this matrix represents. So this corresponds to x1 plus x3 equals 0, x2 equals 0. Solving for my non-free variables in terms of my free variables, I get x1 equals -x3, x2 equals 0. And so the parametric vector form solution would be -1, 0, 1 times s, where s is just any real number. And so that means that this vector, -1, 0, 1, along with all scalar multiples of this vector, would be acceptable as an eigenvector for -4. So now we'll finish off by doing the same thing for lambda 3 equals 4. So it'll be almost the same thing, but instead of subtracting -4 off of the diagonal entries, we want to subtract +4 off the diagonal entries. So we want to row reduce the matrix where now I'm going to subtract 4 from each of the diagonal entries. And again, using our row reduction algorithm, this row reduces to the matrix 1, 0, -1, 0, 1, 2, 0, 0, 0. And with all of these row reductions, like I said, I'm leaving them out just because there's a lot of other stuff that I want to talk about concerning this problem. But with any of these, if you are curious to see a solution to this row reduction, let me know. I'm happy to send a row reduction of this, or with any sort of things that I gloss over. I'm happy to send you more details if you want to see them. So this row reduces to the following matrix, and again, we want to look at the parametric vector form solution of the homogeneous system of equations this matrix represents. And so again, I solve for my free variable x3. And so this corresponds to the parametric vector form solution 1, -1, 1. Oh, that should be 2. Sorry about that. This should be x2 plus 2x3 is equal to 0. This should be -2x3. And so this vector should be 1, -2, 1. Yes, that is right. All right, so we found our eigenvectors. I guess it's been a chapter or so since we've done that, but we found our eigenvectors. What do you notice about, so I had this prompt in the worksheet. What do you notice about all of these eigenvectors? So given what we've done in chapter 6, so I guess when I say what do you notice, in the context of what we learned in chapter 6, look at these eigenvectors and see if you notice something about them. So it turns out the set of all of these eigenvectors, v1, v2, v3, is an orthogonal set. So notice v1.v2 is equal to 0. v1.v3 is equal to 0, and v2.v3 is equal to 0. So all of these eigenvectors are orthogonal to one another. So it turns out this isn't a coincidence, as we'll see in a second. But what this means is we can diagonalize A in a somewhat interesting way. So if, so what I mean by that is if we let D equal the matrix 7, 0, 0. Actually, what I'm going to do, let's see. I might want a little more room. So I'm going to leave the eigenvalues and eigenvectors of A up here. I'm going to move A over a little bit. I'm just going to give myself, we're going to need a little bit of room here. So what do we know? We know that A equals 1, 1, 1, 5, 1, 5, 1, 1, 5, 1, 5, 1, 1 is symmetric. And we know that the set v1, v2, v3 is orthogonal. So what we want to do next is diagonalize A, but I don't want to use these three vectors. I want to diagonalize A using an orthogonal matrix P. And so remember, an orthogonal matrix is a square matrix whose columns are orthonormal. And so there are a lot of reasons to want to do this. But, well, I'll talk about it in a second. So, I'm going to let D be the following diagonal matrix. And we want to find an orthogonal matrix P. so that A is equal to P times D times P inverse. So remember, if I'm diagonalizing A, right, so this is basically asking me to diagonalize A, but putting a few more restrictions on the matrix P that is sort of performing this diagonalization. Any eigenvectors of A can form the columns of P. They're, right? So like, remember, P is just going to be, column 1 is going to be an eigenvector for 7, column 2 is going to be an eigenvector for -4, and column 3 is going to be an eigenvector for 4. And when we defined how diagonalization works, we actually never specified, that like a specific eigenvector of A had to go in each column. And so I could use these eigenvectors, or I could use any scalar multiple of these eigenvectors. So if I want to find an orthogonal matrix P that performs this similarity transformation, all I need to do is normalize each of these eigenvectors. So we're going to let P be the matrix U1, U2, U3, where U1 is the normalized vector V1, which is equal to 1 over the square root of 3 times V1. So the norm of V1 is the square root of 3. V1 is the vector 1, 1, 1. So this is the vector 1 over root 3, 1 over root 3, 1 over root 3. U2 is the normalized vector V2, which is equal to -1 over root 2, 0, 1 over root 2, and U3 is the normalized vector V3 over that, and that's equal to 1 over root 6, -2 over root 6, 1 over root 6. So what we've just showed is that if P is this matrix, then P is orthogonal. And so then P, we could say, is the matrix 1 over root 3, 1 over root 3, 1 over root 3, -1 over root 2, 0, 1 over root 2. So P here is an orthogonal matrix, and A is similar to D. So we've diagonalized A using a set of orthonormal eigenvectors. And so if we can do this with a matrix, then we say that that matrix is orthogonally diagonalizable. And so it turns out, as we'll show in a second, that every symmetric matrix is orthogonally diagonalizable. So if A is equal to P times D times P inverse, where P is orthogonal. And so remember, orthogonal means square with orthonormal columns, and D is diagonal. Then A is orthogonally diagonalizable. So we just showed, again, an example of a symmetric matrix that was orthogonally diagonalizable. Remember, I said it was not a coincidence that the eigenvectors of A were orthogonal. And so we're actually going to show now that, in fact, any two eigenvectors from different eigenspaces for an orthogonal matrix, or for a symmetric matrix, have to be orthogonal. So I'll write that out, and then it'll be maybe a little more clear. Because where we're looking to go, and what we're eventually going to show, is that basically all symmetric matrices are orthogonally diagonalizable, but eventually we're also going to show, in fact, that all orthogonally diagonalizable matrices are symmetric. But first, to do that, we want to prove the following theorem, that if A is a symmetric matrix, like we had in the last example, then any two eigenvectors v1 and v2 corresponding to distinct eigenvalues, so non-equal eigenvalues lambda 1 and lambda 2, are orthogonal. So like I said, with this theorem we want to prove that what we saw in the last example, in fact, was not a coincidence, that we would have expected that to happen. So the way we're going to do this is we're actually going to show the following, that the following property is true. We want to show that lambda 1 times v1 dot v2 is equal to lambda 2 times v1 dot v2. If we can show that this is true for every symmetric matrix, this will imply that v1 and v2 must be orthogonal, as we'll see in a second. So with this proof, again, I've outlined kind of the steps to do it, so I would pause the video here, try to work out the steps on your own. All right, so the way we're going to do this is we're going to start with one side of this equality. So we'll start with lambda 1 v1 dot v2, and we will work our way to the other side of this equality. So the first thing I can do is apply the definition of the dot product to turn this into an actual matrix slash vector product of v1 transpose and v2. So remember, this is equal to the dot product. I think the dot product is just better notation for this. Then, given that lambda 1 is just a constant, this is equal to lambda 1 v1 transpose times v2. But remember, since lambda 1 is an eigenvalue of A and just a constant, right? I can actually bring this transpose out like this. Right, so this is lambda 1 times v1 quantity transpose, since the constant doesn't really affect anything. But now what I can do is I can replace lambda 1 with the matrix A. So a little bit of trickery there, right? We managed to turn this into this using kind of the properties of transposes, and then we used the definition of what it means to be an eigenvalue. Well, this is equal to, now we're going to sort of reapply the transpose, v1 transpose times A transpose, this just follows from the definition of transposes, times v2. But what do we know? And this is the sort of step that relies on A being symmetric. We know that A is equal to A transpose. So this is equal to v1 times A times v2. And just like magic, we've taken this expression, which only had lambda 1 in it, v1 times lambda 2, v2, and this would be v1 transpose, sorry. And v1 transpose there. And we've managed to extract a lambda 2. Well, since lambda 2 is just a constant, we can factor lambda 2 out. Like that. Well, and now we just reapply the definition of a dot product. And following this long string of equal signs, we have shown that lambda 1 times v1 dot v2 is equal to lambda 2 times v1 dot v2. So, why does this prove the theorem? Well, this means that lambda 1 times v1 dot v2 minus, and remember each of these are scalars, lambda 2 times v1 dot v2 is equal to 0. That means if I factor out lambda 1 minus lambda 2, I get that lambda 1 minus lambda 2 times v1 dot v2 is equal to 0. But remember, lambda 1 and lambda 2 are distinct. So that means this number in the parentheses here cannot possibly equal 0. So I have something that cannot possibly equal 0 times something that I don't know the value of is equal to 0. That means this thing that I don't know the value of quite yet has to equal 0, and the proof is done. That is that if A is a symmetric matrix, then any two eigenvectors in A must be orthogonal if they are corresponding to distinct eigenvalues. And so notice we needed the distinct eigenvalues here in this step to guarantee that this difference is 0. We needed then A to be symmetric in this step where we got to get rid of the transpose. So as we will eventually see, like I said, we're almost at the point where we'll kind of see that every symmetric is orthogonally diagonalizable, but I'll go ahead and state the theorem right now. So we'll eventually see that even if we've got, we'll eventually see that, well, like I said, every symmetric matrix is orthogonally diagonalizable. And so I'll state sort of the main theorem right here, that a square matrix A is orthogonally diagonalizable if and only if it is symmetric. So in fact, the only matrices that are orthogonally diagonalizable are those matrices that are symmetric, and the only matrices, and every symmetric matrix is orthogonally diagonalizable. So the thing we haven't shown yet, what I was trying to say before I kind of got a little turned around, so we know that eigenvectors corresponding to distinct eigenvalues, right, have to be orthogonal. We still need to consider the case where, for example, A is a 3x3 matrix, but only has two distinct eigenvectors. So we still need to do a little bit of work to convince ourselves that this theorem is completely true. But what I want to end with is by showing that if the matrix is orthogonally diagonalizable, then the matrix is symmetric. So if the matrix is orthogonally diagonalizable, then it is equal to P times D times P transpose, because remember here P is, well, we'll do P inverse, which is equal to P times D times T transpose, because P is an orthogonal matrix. And so using this, what we can do is say that, well, actually, we can just do it here. This is equal to, it turns out, P times D times P transpose, because the transpose of a diagonal matrix is the same matrix, and P is equal to its transpose, and this is equal to A transpose. So at least one direction of this we have, that every orthogonally diagonalizable matrix has to be symmetric. But we'll look at a few more examples next video. And I do apologize for this video going so long. Sort of the way this chapter worked out, it didn't make sense to do three videos, so there will only be two.